Hi there, my name is Adam Lake, and I'm here to talk to you today about scalable real-time ray tracing on Intel Alchemist GPUs. I'm a software engineer in the GPU rendering team at Intel. So I've divided this talk into two main sections with a couple of subsections. The first one, I want to basically give a primer on the DXR API, and then I want to map that to our hardware to just give you background and set the context for some of the optimizations that I'm going to talk about in the next section of part one. And that section is going to include acceleration structure optimizations as well as shader optimizations. For the shader optimization section, I'm going to do something a little bit different where I'm actually going to show some example case studies of code that we've seen in the wild as we've been doing optimizations over the past year with our ISVs on our GPU, and kind of give you suggestions for what we can actually get in terms of performance in real-world applications with those optimizations. The second portion of the talk, I'm going to transition to talking a little bit more about the future and the vision for what we see, which we're calling scalable real-time ray tracing, and some of the work that's going on in our research labs to enable such a future. So I want to spend 2 slides before I talk about our hardware to just give an introduction to the DXR Programming Model, which is what we use to write ray tracing applications on our GPUs. Also, there's a set of Vulkan extensions called the Vulkan ray tracing extensions that work, that would have a similar set of function signatures as well. So the first thing that I want to talk about is what this API looks like on the CPU side. So we all probably remember how dispatch works for compute shaders. We essentially specify an XYZ dimension for the waves or the workgroups that we want to launch on our GPU. And then on the GPU side, we specify how many threads we want per wave or per workgroup. The way ray tracing works is we're going to extend that API with a set of shader records. And what this set of shader records does is specify what code we want to execute on our GPU when a ray triangle intersection occurs. There's a couple of other things that we need to provide in order to enable ray tracing from the CPU side. One of them is the acceleration structure. And this is broken into 2 components. There's the top level and bottom level acceleration structure. The top level acceleration structure holds pointers to the lower level or the bottom level acceleration structure. It also has a few things like build flags and pointers to the instances or the handles to the objects on the bottom. And in the bottom level acceleration structure is where our triangles or actual geometry lives. There's actually additional build flags and things like a matrix transform. So when a ray enters the bounding box for one of those bottom level acceleration structures, we can actually do the transform from world space to object space. The final component to bring this all together on the CPU side is something we call the ray tracing pipeline state object. And this is similar to the raster pipeline state objects where everything else that's needed to render an image is part of the ray tracing PSO. Now on the GPU side, we have new shader types that are introduced with the ray tracing pipeline. And the next slide, I'll kind of animate these and show what points they're exercised. We have one kind called we name the ray generation shader, and this is what's used to generate rays on our GPU. And then we have a few different ones. Any hit shader, which represents any hit that happens with the ray. The closest hit shader, again, it's what it sounds like. It's the one executed one time per ray on the closest hit. Miss shaders are if you miss any geometry. And there's also intersection shaders, which allow you to do procedurally user-defined primitives. We're not going to talk much about intersection shaders today, but the other shaders we will talk about when we talk about shader optimizations. The other thing that I want to mention is whenever you're actually doing an implementation of a ray tracing pipeline, you really need to wrap your head around some of the shader record indexing. This is one of the key new things that are part of the ray tracing pipeline. Those equations are specified in the DXR spec, but there's also a really good article by Matt Usher in Ray Tracing Gems 2 that I provide a reference for at the end of this talk that walks you through how to use those. Basically, it's a handy guide for how to understand how a shader record indexing works. Okay, so I've talked about these new shader types on the previous slide. And now I want to kind of show this visually and animate how they operate in the scene. Here on the right-hand side, I have a simple pinhole camera, and we've got this grid of pixels that are cast out in the scene. Y'all graphics folks know this image. And the ray generation shader, what it's going to do is generate rays that are going to trace through the center points of each of these pixels out into the scene. And this ray generation shader is executed on the GPU. In this case, we're going to have a ray that traces through the center of the pixel. You can see this green ray, and it hits this bunny in the scene. And at this point, this is where we're going to actually execute two of these shaders. One is the closest hit, and the other is the any hit shader. Both of those are going to be executed at this point and use that ray triangle intersection that comes back from this from the bunny model. This step 3 is actually a little bit different. Here we're hitting this magnifying glass, and we're going to, just as we did with the bunny, we're going to execute the closest hit and any hit shader, but that ray is actually going to continue out into the scene and hit this other statue, which at this point, because we've already executed our closest hit shader, only the any hit shader is going to be invoked. And then finally, this ray traces through the center point of that pixel out into space, and we call this a miss shader because it didn't hit anything in the scene. And in this case, we'll typically just have a very simple color value that we'll use for the background, or maybe a lookup into an environment map to decide what the final color for that point is. One other thing to mention here is all of these shader types are optional to execute. And the other thing is we have flags that we can optimize these structures so we can have an early exit. For example, when we hit the bunny and we know we don't have any, maybe we don't have an any hit shader at all because we just hit that rabbit, and we're not going to need to move that ray any further in the scene, so we can go ahead and early out on that. So now that I've given an overview of the API, I want to show how those different components map onto our hardware. On the right-hand side, I have an image of the key components of the ray tracing hardware and how this is put together. So first, we see on the upper left these orange boxes. These are being executed on the what we call the Xe vector engines. And these are what support the SIMD ISA that we know and love on our GPUs. And all of those all of those different types of shaders are executed there. We also have and this is also the code that you as the programmer write. In blue, these are the hardware units. These are typically programmed by the driver. These aren't programmed by the API itself, but they're a key component to getting the performance that we have, and you can see some of the traversal and intersection units here. The final component here on the right-hand side is all of the state that we need to manage. And for ray tracing, we need to manage a lot of state. Every ray is going to have its own state. You also have all of your geometry, including your BVH nodes and the shader tables that I mentioned previously. So all of that's contained in memory, and those are the green components on the right-hand side. Now that picture is a little bit misleading because it doesn't tie, I want to expand the scope here, basically. We don't just have one of those Xe vector engines. We actually have 16 of those on our GPU. And for the purposes of ray tracing, those will be usually in SIMD8 or SIMD16 mode. And then we have the dedicated BVH cache, and this is the every Xe core has a dedicated BVH cache, and this provides fast access to our acceleration structure. And in terms of throughput, we have a combined throughput of 1 ray per triangle intersection per clock, or 12 ray box intersections on each Xe core. And just to give you a flavor of the different SKUs of hardware and how many Xe cores are there, I basically mentioned here, hey, we go all the way from 6 to 32 of these for the Alchemist GPU line. And I already mentioned previously, but just as a reminder, these are available via DXR 1.0, also DXR 1.1, and the Vulkan extensions. I'm going to talk a little bit about the differences between 1.0 and 1.1 on our GPU in the performance optimization section. Okay, so what I want to do now is do a deeper dive on what are critical hardware units to understand, in particular to lay the foundation when I talk about performance optimization, to motivate why those optimizations are important and how they're working on the GPU. So this is a nice representation. There's a picture on the right-hand side. And just to kind of walk you through this, effectively, we have this unit that's called the thread sorting unit. And what this does is allow us to take a set of rays. So I want to take a step back. Our hardware unit was designed with incoherent ray tracing in mind. You know that the first ray generation shader that you typically lay out, all the rays are nice and coherent. You're going to get high performance, high SIMD utilization. But as soon as you hit a surface, all of those rays scatter wildly out into the scene. And so what we want to do is when we know what those rays are going to hit, we're going to actually repack those rays and basically any ray that has a shared shader record, we want to pack them in the same SIMD packet and send those back to the vector engine to get full utilization of our SIMD units. So that's what the thread sorting unit is for, and you'll see where this comes into play later in the optimization section. The other thing that's important to point out is what the limitations of the thread sorting unit are. And the key point here is for Alchemist, we have 128 sort keys. So this is an upper limit, and it's something you want to keep in mind when you're doing optimizations for our GPU. Now I want to take you through what happens we'll call this the myth versus the reality, or the model versus the reality of what actually happens when we call trace ray on the GPU. So in this picture, I have the model of, hey, you call trace ray, and basically this is executing over time, and you're just waiting on the GPU. You could call this a synchronous style of coding, where you're waiting for the result to come back, and when it comes back, you continue executing that function. But that's not actually what happens. What happens in reality is a few different stages, and this is a better visual of what happens. So when we see a trace ray call, we actually want to save the state of the current shader, and then we're going to load that back in to memory later after trace ray is finished. So at trace ray, we're going to store all of the state in the shader off into memory. Then the thread sorting unit is going to be called and execute those shaders. Whenever we have intersections, repack them and execute those functional units again. And you see that in the orange, yellow, and blue boxes where the thread sorting unit is effectively repacked or resorted the rays and executing them back on the vector engines. And then finally, we're going to reload after trace ray and continue on with execution. So you can see there's a lot of memory interaction here, as well as the hardware units engaging at that trace ray call. So there's a lot more happening here than what looks like when you just call, when it just looks like an API call to us. One final point I want to make is we now have support in GPA for DXR. You can effectively select a dispatch rays call and visualize a number of components. There are additional features coming online for ray tracing in the future. So now that I've laid the foundation of what our hardware looks like and how the DXR API maps to the hardware, I want to talk about a number of performance optimizations. And something that's different than you might see in our performance guide or other performance guides that you've seen from other vendors is these are actually, what I've done is lifted out the ones that we are actually seeing in practice over the past year when we're doing optimizations with ISVs. So I want to highlight those, and I'm actually going to give some specific examples, in particular when I talk about the shader optimizations of things we've seen in practice. So I've bucketed these into two big categories. One is around acceleration structure traversal, and this is going to be talking about bounding volume hierarchies and building those and putting the geometry in the right place and doing the right things with our geometry. The second part is about shader execution. So this is, we're going to be talking a lot about that thread sorting unit and how we can best get the performance out of the thread sorting unit. And then the final piece here, I'm actually going to share some performance numbers from things we've seen in practice when we've put those shader optimizations into play in ISV actual games that have shipped into the world. Also want to mention, there's an additional set of optimizations in addition to the ones that I provide today in an optimization guide, and I have a link to that at the end of the talk. So getting into our best practices for acceleration structures, I want to talk first about flag usage. And this is going to benefit on all the GPUs. Microsoft mentions this in the DXR spec even. Always prefer fast trace for static access and for top-level acceleration structures. This is a pretty known thing in the field. But the couple of these other ones that I highlight in red are maybe a little bit focused on our GPU in terms of actual negative performance impact. The no duplicate any hit invocation geometry flag actually is going to require that the implementation guarantees only once per ray any hit invocation. And this can actually result in a double-digit performance loss because of the record keeping that has to happen for that. The other flag to try to avoid using is the build flag allow update. Here, again, you're going to have an additional memory footprint, and it's going to impact your performance if that needs to be kept track of. The other point to be made is, while this is going to slightly increase your per frame cost, we do recommend building the top-level acceleration structure every frame. This will stabilize the performance and reduce the per frame variance, which is generally more desirable than having a jitter or a stutter in our frames as we're presenting them on the display. Now, the next thing that I want to talk about is perhaps more specific to our GPU and how we actually process geometry. We don't actually do a per triangle ray triangle intersection. We actually optimize in terms of what we call a quad. Now, this quad isn't a true geometric quad. It's actually just two triangles that share an edge. In other words, they don't have to be coplanar, but they do have to share that edge. And this allows us to use index geometry, and we have the index geometry. We can get this better throughput because we can form these quads instead of having to do it. When we can't form the quad, we're still going to push it down as a quad, but we're going to do a degenerate triangle for the triangle on the other side of the edge. So another counterexample here is things like don't use stream output because this produces a disconnected mesh, and just avoid disconnected triangles in general, because if there's no index reuse, you're not going to get any quad formation. You're not going to get maximum throughput of our BVH traversal. In order to get this good triangle or good indexed geometry, we actually recommend you use any vertex cache optimization algorithms. These were popular in the late 90s, early 2000s. We haven't talked about them much in recent years, but they are important for us to get the best performance. These produce triangle orderings, which maximize our local vertex cache reuse, and also they're ideal for the quad formation. We also recommend a 16 triangle window if you have control over that. That's a sweet spot for our GPU. The other thing is, if you don't already have a vertex cache optimization as part of your toolchain, there's a good open source implementation by Arseny Kapulkany. The link is here. We recommend you take advantage of that in your pipeline. Final point here is, if you are doing GPU generated geometry, do the geometry generation in one pass separately from the ray tracing acceleration structure in a second pass. Interleaving these does not allow us to get as much parallelism out of the acceleration structure generation, and so it's not going to give you as good of performance. It ends up serializing the BVH build, and you lose performance that way. So a couple words about geometric representation on a GPU. We've seen a few games, and when they load a level in, one of the things they'll do is they'll take objects that aren't necessarily part of the scene right away, they'll load all the geometry, and they'll kind of store it off screen. And this makes sense when we were doing rasterization, because anything that was off screen, we have a culling algorithm. It dismisses all of anything that's the BVH isn't within the view frustum, and it doesn't really have a performance cost. But in the case of ray tracing, if any ray finds that geometry in the scene, it's going to end up bouncing around in there, and you can actually cause a TDR if even a single ray in the scene finds that geometry. So avoiding this overlapping case where we load the scene and we put all our geometry somewhere, or just avoiding this overlap in general, is a good practice. The other thing that's a good practice is to try to avoid empty space. And one way this empty space, we've seen it manifest, is an animated object, or consider like an animated character that's running. When they start off in their pose, their legs are close together, and this looks like there's not a lot of space there in the bounding volume. But as they run and the animation happens and their arms are splaying out, also you're ending up having a lot of open space there. So that empty space is going to reduce performance. And to kind of get around that, having per object or smaller BVHs on each of those objects will actually give you better performance than a single BVH on any two pieces of geometry that are going to have a lot of empty space between them. Another thing that we've seen in some of the engines is we'll have a mesh, and in this case we have this bunny, and imagine this bunny had ears, eyes, a head, its body, a tail, and the legs, and they were all individual BVHs. This is a good case where all of these things have a static association between them, and merging them into a single BVH is going to give you a significant performance speed up. We've seen when we've done this in an engine and merged objects like this, up to 2x performance increase by putting this into practice. Another point here is to avoid large skinny triangles, because those generate large bounding boxes. And those also, as I mentioned previously with the empty space, can result in a performance degradation. Okay, I want to move on now and talk a little bit about barriers. And this is actually adopted from some of the sample code that we've seen online. And for the case of this sample, it was actually not, it wasn't anything that was, it's a small piece of sample code, but we've seen then this pattern emerge in other engines. The key point here is, rather than having a single scratch resource where we basically try to create one scratch resource that's the maximum size of any BVH construction that we need, if you do it that way, you're not actually going to get the best performance. Instead, if you have a per object or per BVH build scratch resource, so you're trading your memory for increase in memory for an increase in performance, you can actually do all of that in parallel. The other thing you can do, and this example on the right-hand side shows this, is you can actually get rid of the barrier call because you're not sharing the same scratch resource anymore. So all of those things can be done in parallel, and you don't need the barrier until you're finally waiting before you need all of that geometry completed. So you're going to get much better performance if you think about this whenever you build your engine. So another point I want to make here is about alpha-tested geometry and hit shaders. This is another example where there's a lot of empty space, but the use case is a little different. This is for alpha-tested geometry. The previous case was just empty space with normal geometry. So here, whenever you're using alpha-tested geometry that's implemented as textured triangles in any hit shaders, and the geometry contains these large transparent regions, it's a good idea to go ahead and subdivide that, and we kind of show this visually on the right-hand side. Subdividing it's going to provide you better performance than if you have this large expanse of empty space in that same object. And I want to touch on some of these ray flags. I went to one of the things that we were mentioning to folks in the optimization guide is to use as many ray flags as possible. This is also part of the optimization hints from the Microsoft spec. And I said, hey, that's nice, but there's a lot of flags here. Can we help give better guidance? And I got some great feedback from our internal teams here. They were saying, hey, one thing is obviously passing these in as compile time constants so the compiler can see them. That's good. The other one is around this force opaque and force non-opaque. It kind of turned the contrast up on these both to me. In the force opaque, they say, please use this flag because we can optimize knowing only one any hit shader is invoked. However, similarly, please don't use force non-opaque if you can avoid it. This is because the ray is going to assume you can have an any hit shader for every triangle and has to check every single triangle. And often you only want the non-opaque flag on transparent geometry. So now that I've talked about some of the performance optimizations and performance hits around acceleration structures, I want to transition to shader optimizations. But for this section of the talk, I want to change the style a little bit. Rather than giving an overview with some visual representations, I'm actually going to show some coding samples. So here on the slide on the left, I've got what we've seen in practice. And what I've done here is built a case study out of 3 or 4 different patterns that we've seen from different vendors. So this isn't any one specific ISV's code, but it's representative of the workloads that we've actually done optimizations on in practice. On the right-hand side, I'm rewriting that code. So you'll see these transforms, about 4 of them that I want to walk through, to go from what we'd call an unoptimized or a set of anti-patterns for our GPU to a set of good programming practices on the Intel Alchemist GPU. So first thing is, looking at this ray payload, there's actually 2 optimizations that take place here. The first optimization is the observation that we had a bunch of flags. Every one of these is a float3 vector that was being passed as a ray payload from one shader to another. This is going to negatively impact performance because that's a lot to carry around. If you remember back on the picture that I was showing how everything's laid out, all of this state has to be held in memory, and you have to fetch this to and from memory every time you want to access it. The second optimization here is the observation that I didn't actually need full 32-bit floats for the color here, and I could actually relax that to 16-bit floats. So with that put into practice, you can see a huge reduction in the number of bits that are basically needed to represent this ray payload. The second optimization is around this color value. So if you look on the left-hand side, after trace ray, we actually had to have the color value be pulled in from the top, from above the traceray call to the bottom, and this is part of that spill fill load where the color is used before traceray and after traceray. So the first thing we did here is lower this down into the closest hit and miss shaders, since effectively that's what that code was doing on the left-hand side. So again, the motivation for this is to reduce that spill and fill cycle that we had to do whenever we call traceray. And then another optimization that we have here is there was this render target store taking place at the end of the shader, which again required us to come back to the ray generation shader, even though all we were doing is storing this value. So what we do here is we actually push that store down into our closest hit and our miss shader. And then for the final optimization here, what I'm going to do is, instead of pushing over to the right-hand side, I'm going to take the code on the right-hand side, move it over to the left, and do one more optimization to make this. And oh, by the way, this is actually a fully tail recursive shader at this point on the right-hand side. We don't even have to come back to the ray generation shader at all. So the final point here is to get rid of the payload altogether. And so I know on the previous slide, we did a bunch of work to compress or reduce the amount of the payload passed. Here we get rid of it entirely by just doing the load in the closest hit and miss shader. So by putting all of these things into practice, we've actually seen quite a bit of performance speed up. And I provide two examples here from real workloads in the real world. So one of them is putting this tail recursion that I talked about in place. We've actually seen around a 9.5% increase in performance. This was on a global illumination specular shader. And the other is minimizing the spill data that we had to do the spills and fills on. We've actually seen over 16% increase in a global illumination renderer. And I was sharing these results, discussing this with some of the folks in the performance team. And another thing that they saw in the past year, they've had at least 2 workloads, and they said, you've got to tell people about this and make sure they know about this. So, and this is a pretty simple idea. In the workloads we saw, we were passing in a loop count as in the constant buffer. And the problem is that isn't actually visible to the compiler, so the compiler can't do any optimizations on it, even though in both of these cases the value was like a 1, 2, or 3, or a 2, 4, 8, 16, and these are reflecting either the number of reflection rays that were being passed in, or like a path tracing solution where we only had 1, 2, or 3 passes depending on the visual quality we're trying to achieve. So in the case of a shadow pass, by replacing these loop iterations as constants visible to the compiler, we got around a 17% increase, and we had a 28% increase in a global illumination renderer by replacing these constant buffer values with constants. And the thing is, you don't actually have to rewrite your shader multiple times for this. You can see this little piece of sample code on the right-hand side. You can just add a define to the DX shader input parameters and basically hard code that as a 1, 2, 3, and generate 3 unique shaders for each of them. So you don't have to have 3 of those pieces of code sitting around in your HLSL code. You just send a pound define in for each of the instances. So now what I want to talk about is some of the difference between what we call an asynchronous style of ray tracing, which is what DXR 1.0 enables, and a synchronous style, which is what DXR 1.1 uses. So I have these pictures on the right-hand side to kind of motivate some of the problems with this synchronous style of ray tracing. And so if you look at the top image, this is kind of showing what the problem is, where you can see we have our ray generation shader launched, and then we're going to call ray query. Ray query is effectively this replacement for the trace ray API that is used in the 1.0 implementation. And what happens is 2 problems. The first problem is that ray is occupying that thread, and it never evicts itself. That's very different than the trace ray call. If you call a trace ray, we have a spill and a fill cycle. So whenever trace ray is called, we're able to effectively relinquish that thread, and until we have more work for the vector engine to do, we can use that vector engine for other threads that might want to run and execute on the GPU. So this is the first thing. That the problem is we're basically hogging the threads on the vector engine. The second problem is the worst case scenario, which is shown in this long running ray tracing thread, where none of the threads can complete until the longest running thread is done. So again, we're not going to have that problem whenever we are using the traceray API, because everything's asynchronous, and And the way the thread sorting unit is working is once it has enough work that can leverage the same, can be packed into the same SIMD unit, it's going to go ahead and issue that back to the vector engine for execution. So you can see how this manifests in practice in terms of performance, where on the bottom you have your ability to do ray tracing, but you can also insert additional work because there's going to be a reduced latency with the 1.0 pipeline and maybe do some additional asynchronous work versus having the situation when you have the synchronous style ray tracing on the top image where you're effectively stalled on the GPU and nothing can execute until all of those synchronously executing shaders have completed. So here's another thing that we often see from ISVs, and this happens for us for both ray tracing and rasterization, is assumptions about the SIMD wave width on the GPU. So the key point here is don't write shader code that assumes a 32 wide SIMD wave. On our GPU, we're going to actually compile to an optimal SIMD size based on a few different characteristics, which include things like register pressure, how much group shared memory you're using, and other factors. So we actually will compile SIMD 8, SIMD 16, or SIMD 32, depending on the scenario. Another thing is that there's actually ways that you can determine this on the CPU side. If you want to determine if the SIMD size of less than 32 is supported, there's an option called wave lane count min, so you can query this on the CPU to determine this. And a final point to make here is if you know that your wave size is required to be size 32, you can actually force this with a feature in Shader Model 6.6, and we will honor that and compile to a SIMD 32 wide wave. That doesn't actually necessarily give you the best performance, but it will be functionally correct. The final recommendation here to give you better performance is to use the wave intrinsics instead of the barriers. Some of the barriers will actually force all the waves to wait for the longest running wave, depending on how the code is written, and this is not going to be the case if you use wave intrinsics. And another point that I want to make about using implementation of ray tracing, and this actually impacts both a 1.0 pipeline or a 1.1 pipeline, is the use of asynchronous compute and ray tracing. So the key point here is that the memory that's used for group shared memory, which is used in our compute shaders, and the ray tracing acceleration structure leverage the same L1 cache. So you're going to get reduced performance if you use group shared memory. So the key point would be to try to avoid the use of group shared memory in either the compute shader that's executing the ray query call that you're using, or if you're trying to schedule work asynchronously, any work that you schedule asynchronously, try to avoid the use of group shared memory for best performance. Now, you might say, okay, that's a lot of optimizations that we've just talked about. We actually have a whole bunch more. But and these will be covered in these are covered in our performance guide. But what I wanted to get across to you were things that we actually have seen in practice, and I shared some of those results and things that we see that have a high uplift for you to put into practice today. So if you don't remember these things or you want to look for more details, there is an optimization guide. The link is here, and I encourage you to read that to get, refresh your memory on these things and put some of these into practice in your implementations on our GPUs. Okay, so the first part of the talk was largely focused on our GPU today, how it's built, and some of the performance optimization patterns that we've seen, putting those into practice, and some of the performance improvements we've seen in game engines over the past year. Now what I want to do is turn an eye towards the future and talk about something that we call scalable real-time ray tracing. And I want to put that into context by two things. One is I want to explain what I mean by that. The second thing is I want to talk about some of the things that we're doing in our research labs to help realize this vision of the future as well. Okay, so I want to motivate this visually, and here on the screen we have two images from the same engine, and these are courtesy of Ghostwire Tokyo. And on the left-hand side, I've highlighted in yellow this reflection that you see in the image. Also on the right-hand side, this is the same reflection, but it's done with ray tracing. The one on the left is a screen space reflection, and you can see the visual quality isn't as quite the same as the ray traced, more photorealistic looking scene on the right-hand side. And these are like a glossy surface. It's kind of like a rainy night, and so there's a little bit of shininess here. So you want to see that really crisp image on the ground plane there. That's one problem, but this is the problem that I find as a game player the most visually distracted with screen space techniques. Here, what we've done is we've tilted our head down slightly, and when we've done that, the the surfaces or the materials that were generating those reflections are off screen. And the result is a screen space technique doesn't pick them up anymore, so you lose them. However, as long as they're represented in the bounding volume hierarchy for ray tracing, you can see that you're going to continue to have that higher quality reflection there on the scene. So the point here is that, if you look at the image on the left, that's not how the real world works. It works the way the right-hand image does. And I want to see more engines and more simulations for game players that look more like the right-hand side than the left-hand side. And we have to think of ways that we can do that. So what I want to talk about now is this idea of scalable real-time ray tracing effects. What I would like to see us as an industry move away from is relegating ray tracing only to our high-end GPUs, but instead start to think about implementing them as scalable solutions that don't just work at the high end, but also work on our mainstream solutions and eventually the low end. The long-term vision is to eventually get rid of any of the effects in the rasterization pipeline, but I realize we're a long time from that today. So I mocked up this UI just as an example of the kind of things that we could do in an engine. And the reason I think this is important is we're not just giving the programmers and the artists control over the scalability, but also empowering users on the platform to be able to control this themselves. So just as a few examples here, I've mocked up this little reflections interface. And the idea is, first of all, you can turn the reflections on and off completely with this radio dial. But the other thing here is you have these slider bars with a few different parameters that impact the performance and the visual quality trade-offs that a game player might make in the scene. So in this case, we're saying the number of reflection rays per pixel, the LOD resolution, or the object range to include in the BVH. I'm going to come back to this object range on the next slide and show a little bit of data on some experiments we did. But I just want to highlight that all of these things are things that are easy to control and provide a high impact to the user to feel this sense of empowerment of, they're able to influence this and see the visual result on the screen and play with this visually. I also think this can be done for shadows, ambient occlusion, things like global illumination. I don't want to prescribe the set of parameterizations here today, but what I want to do is motivate this concept of having the ability to have all of these different parameters input to our ray tracing pipeline and implement them in a scalable fashion so that they can be empowered to have control over these features. There's some games out there in the world that have done some of this in practice, and one of them I'm sharing here, where effectively this is going back to that object BVH range. And the idea here was really simple, but it was also a very powerful effect, where the number of objects, I show this image on the on the left-hand side with a camera, and the basic idea here is, imagine a slider bar that goes from 1, 2, all the way up to 10, and as it expands all the way up to 10, effectively 10 is saying have all of the content that the user can see, and even things off screen that they can't see as part of the BVH. And you're going to have a size that's proportional to that, a lot of objects in the scene. But then you can imagine on a lower end GPU, maybe you just want to say, well, just have the objects that are closer to the user. So if you go back to that Ghostwire image scenario, you're still going to pick up those reflections of the objects that were very near to the player, as you saw, but maybe something that's far off in the distance might not be picked up. And I just saw this in a game, and what I did here is increase the number of objects in the BVH just to get a sense of going from 1 to 10, and saw this nice roughly linear increase. The specific numbers aren't important. The idea is this general idea of increasing the number of objects in the BVH, and the BVH size was increasing proportionately. So this is the kind of thing that would impact obviously the memory utilization on the GPU, which is related to the performance that you'd see. So I like to see games like this. And one game that we actually saw to put that into practice was Spider-Man Remastered and the Miles Morales series. Both of those games do something similar to this, so check those out, because I think they did a good job of thinking about this concept of scalability with real-time ray tracing. Then a final point I want to talk about here in terms of scalability that of course we got to talk about is XeSS. XeSS has a pretty significant impact, and we've already seen this in a number of games. As you can see here, there's 5 different titles with both a balance and performance settings, and in some cases we're seeing a 2x performance speedup by using XeSS as an upscaling solution with our ray tracing pipelines. So there could be an entire talk obviously dedicated to XeSS, and there is, so look for that as part of this series. I'm going to not say more about this, but I do think that that's a great talk to take a look at if you want to know more details. For this last part, I've now laid out this vision for what we mean when we say scalable ray tracing, and I want to talk about some of the things that we're doing internally in some of our research to enable this future. I want to also mention, we're not committing to any kind of products or roadmap today, but they are things that we're exploring in our research labs, and we are looking for collaborators. So we'll give some email addresses at the end if you're interested in talking to us more about building any prototypes or proof of concepts with us. We'd love to have some interaction with you and have that take place. So I want to talk about ray tracing level of detail. I think intuitively, or from our backgrounds, we all know what level of detail is. The basic idea is we have either for our geometry, textures, we have different polygon counts or different resolution of texture for level of detail. And in the context of ray tracing, because we know the cost of traversal is a key contributor to performance, if we reduce the number of triangles in our LODs, we can improve performance of our acceleration structure traversal. Now, there was a paper by Brandon Lloyd and some co-authors in 2020 about a feature that they called stochastic level of detail. Now, this has been used in rasterization before, but it was never really discussed in the context of real-time ray tracing APIs, the new APIs like DXR and Vulkan, until this paper came out. And the basic idea here is on a per-ray basis to decide whether we're going to trace a low LOD representation of our geometry or a high LOD representation. And the basic idea here is shown nicely in this image from their article on the bottom here, where there's this mesh. On the left-hand side, there's let's say a high-resolution representation with that kind of dark red color transitioning over to the right, where all of the rays are hitting the lower representation in the brighter red. And the idea here is to cross-dissolve. And rather than having a discrete LOD where for every ray you're going to either hit the high LOD representation or the low LOD representation, to instead be able to control this on a per-ray basis. And this is a very nice feature. Key point is it's going to be a smoother transition than discrete LOD. And I have some videos towards the end here that I will show to show that result. So we implemented this on our GPU, and you can see some of those performance numbers on the right-hand side. I'm not getting into specifics of whether the discrete or stochastic was faster. The key point is seeing a nice sizable improvement transitioning from having no LOD solution to implementing this technique, whether you chose discrete or stochastic. However, there are some downsides to this technique. One of them is this is limited because of how this is exposed in the DXR spec. You only have 8 levels of transition because you're leveraging this instance mask. The other downside of how this is designed is if you use your instance mask for LOD solutions, you can't use it for some of the original intended use cases. If you go back and look at the DXR spec, there's some of the descriptions of things like, maybe the way I'd phrase it is high level passes over the same acceleration structure. For example, things that you're doing a shadow pass. So you want to know only the shadow casters. So you may use the mask to mask out things that aren't shadow casters to be included in your ray tracing acceleration structure traversal. And what you've done is you've effectively hijacked that mask to do ray tracing LOD, and you can't use it for some of those original use cases. So what we're thinking about is, can we actually do something better? And we want to solve 2 problems. The one is to introduce a new comparison operator that allows that instance mask to be preserved for some of its original use cases. And the second thing is we want to get around that limitation of only 8 LODs. So in this case, we're kind of prototyping this idea of having about 128 comparison values. And the other idea here is you can actually switch the operator to be either a less than or equal to or a greater than. And the idea here is if you're looking down the positive Z or minus Z axis, it's simple from a functionality perspective to integrate it into your engine. So we think this can actually effectively get rid of the disadvantages of the stochastic LOD solution as it's described today and provide more flexibility to users. So that's laying the foundation for stochastic LOD. And now I want to talk about another technique that we're working on in the research labs, and this is called traversal shaders. So the basic idea here is this is a new programmable shader stage, and we've actually published a couple of papers already in the academic literature. Those references are linked here as well. And the idea here is to be able to procedurally select which BVH we're going to use during traversal. Another important point here is you can mix this with the existing hardware instancing solutions. So this isn't a thing where we're saying do this instead of that. We're saying you can do this in addition to the other techniques. And another thing that I think is really powerful here, and this might be the most important part of why traversal shaders are such an exciting innovation, is this concept of effectively bringing the power of the Ray Query API and the procedural nature of being able to, issue a Ray query from a compute shader and kind of bringing that into the 1.0 pipeline. Because if you recall, if you use Ray query, you aren't able to use our thread sorting unit. But here, what we're effectively doing is bringing that thread sorting unit back in to get that peak hardware performance and peak hardware acceleration, but using the DXR 1.0 pipeline with features, the best features from the Ray query API. So what this looks like here visually, on the left-hand side, I've got this bounding volume with a top-level acceleration structure and a bottom-level acceleration structure. And I had an image like this at the very beginning of the talk, very similar to this picture. And what we're basically doing here is we're introducing this new traversal shader stage, which is a programmable stage, sitting between the top level and the bottom level structure. And the idea here is, as you traverse the top level and you decide you've hit a bounding box of the bottom level structure, you can make a decision of which low level BVH that you're going to traverse. So why might we want to do something like this? Well, there's a few different reasons. One, we talk about this instance mask a lot, and this comes back here again. This is maybe already be used for somebody else. Maybe the artists are using it. Maybe there's performance reasons that you're using it for some of the algorithms that you're implementing. The other is you may have LOD selection that you want to depend on things like hit distance, which isn't even known at the time of the trace ray call. So the only way to find that would be to do multiple distance estimations some other way. So you don't know which one to pick until you actually are running the shader. And so this is a way to have that determination made after you actually know how far away the object is that you've hit. So what does this look like in practice? Well, I have a little bit of pseudocode here on the left-hand side. And the key feature here is in this code that's executing on the GPU, we have this new call. And it's very similar to trace ray. We call this forward ray. And the key point here is the difference between forward ray to trace ray. The way to think about it is instead of the first parameter being the top-level acceleration structure that you're going to trace into, you're passing a bottom-level acceleration structure that you're going to trace into. The other important thing to know about traversal shader is that they are tail recursive by nature, which is how we're getting back that engaging the thread sorting unit. We no longer have any code after forward ray. It's not allowed to be written into the shader. So once you decide where you want to forward the ray, that's it. The shader then executes end of thread, gets off of the vector engines, and other threads can then come down and utilize them. So a few different use cases here is going back to what we were talking about before, the stochastic LOD transitions. And this would be really useful where we have indirect rays or secondary rays where the primary ray hits the object, and then we want to decide to traverse a lower LOD for subsequent rays. Another is using an LOD bias if we're doing a global illumination solution. We've seen papers even back, even from like 2010 in the film and production studios where they were taking 2 million polygon meshes and then they're reducing the LOD for their secondary rays down to 2,000 triangle objects from 2 million and getting a huge performance improvement there. Another third use case, imagine you're using something like direct storage or you're streaming content from somewhere else on the cloud and you've got a user in this like metaverse simulation. Well, imagine they transition to a new place in the scene and you haven't yet loaded in the geometry. You might have some simple proxy geometry there and a set up like a bit mask that says for every object as the new subsequent higher LODs come in, you can go ahead and enable them. And in this case, your forward ray algorithm and which LOD you pick would be based on the highest quality LOD that you have while they're being streamed in from somewhere else, either again, off a local disk or somewhere off the cloud. So here, I wanted to show what this looked like visually. We've implemented this on our GPUs. This simple sample has 6 different LODs. They're color-coded on the left-hand side in this video. Each one is about a 4x reduction in triangles, and there's 4 reflection rays and 1 shadow. And the idea here is we're selecting which LOD to traverse on a per ray basis. This is running on our Alchemist A770 GPU. And then if you want to see what this looks like comparing 3 different simulations here, or 3 different implementations. On the left-hand side, we've got a set of these Buddhas, and that's the maximum resolution. In other words, there's no LOD. In the middle, we have the discrete LOD, and on the right, we have the stochastic LOD. And the one thing I want you to pay the most attention to is between the middle and the right, where you see that smooth transition of the stochastic LOD solution. Also, that this is being done with the traversal shader implementation on our GPU. So you can see this smooth transition happening. And by the way, the image on the left is running about 100 to 125 frames per second, and the ones in the middle and the right are running between 150 and 175 frames per second. And there's more than 3,600 Buddha instances in this scene. So just a little bit here on the right about performance. When we compare this to the instance mask technique, we see we're basically able to get about the same level of performance of the instance mask. So there's no additional cost, but we have the full programmability that the traversal shader provides. The other thing is we can retain that instance mask functionality for some of the original use cases that it was intended. Okay, so a couple of closing points here. Few things. This is the last slide. We think that rendering is at an inflection point. And we had a big transition when we were introduced to the ray tracing API in the first place. This was a revolution in graphics, the first time we had it, and again, relegated a lot to high-end GPUs. But in the future, where we're transitioning is where ray tracing hardware is going to be mainstream. It's going to be on all GPUs. And we want to start to prepare and think about that as an industry. So there's going to be ray tracing from the mainstream to high-end. The other idea here is the idea of simplifying our art and rendering pipelines. So we no longer have to implement things with both ray tracing and rasterization, but transition to a future where there's ray tracing only implementations. This isn't going to happen overnight. This is going to take some time, but I think we want to start to think about this and put this into place when we can. The third point here is empowering users with control over those parameters. And I kind of showed this mock-up UI of things to think about in terms of giving users control. So if you're interested in hearing anything more about traversal shaders or anything else in this talk today, feel free to reach out to myself or Gabor Lichter. Our email addresses are here, and we can provide more of those details. I also want to acknowledge a whole set of collaborators. I hope I didn't forget anybody. Lots of people helped shape the quality and the content of this presentation, and appreciate the work that everybody's done here.